Bismillahirrahmanirrahim. Assalamu alaikum. This is our third lecture on the topic of complex number, part of your A-level pure mathematics P3 revision. In these lectures, we are covering the summary only, not in detail, but comprehensive and short, brief summary, but very comprehensive about the topic, so that when you start my live session online, so you know the basics of all the concepts regarding the complex numbers, and then we can apply these concepts in various types of questions, especially the past papers question. Right now we are discussing about the roots of polynomials, starting with the quadratic, and if the roots are complex. For example, if I have something x square plus x plus 1 equals to 0, and if I ask my students to solve this, how to solve this? You apply the quadratic formula minus b plus 1 under root b square minus 4ac divided by 2a. That will be negative 1 plus minus root negative 3 over 2, and you can rewrite this as negative root 3 means root 3 with iota over 2. Now, interesting observation here, the roots are in conjugate pairs. You see, the first root is minus half plus root 3 upon 2i, real part with the imaginary part, and the second is minus half minus root 3 upon 2i. And remember this point here, whenever roots are in the form of complex conjugate, the condition says the coefficients in the polynomial all real. Please note down, if you have something like this, x square minus iota x plus 2 or minus 2, then it is not possible to have roots if complex in the form of conjugate pairs. You should be having all the coefficients real in order to get conjugate pairs. Make it a note here, note it down, this property. Every time the complex roots are not the conjugate pair if the equation containing some imaginary coefficient. If all the coefficients are real, in that case, if the roots are complex, then you get conjugate pairs. It's a very important property you should note down. Now I can show this with the help of some graphs here. You see here, if you have a degree 2 of equation quadratic, the roots are alpha and beta, you can write the factors form. If you solve equating by 0, and you should know the meaning of the roots. Roots are the point where the curve cuts the x-axis, the y value becomes 0. So you may be having two real roots, or possibility is there that you have just one real root. That is, the x-axis becomes the tangent, or you can say the real axis becomes the tangent if we talk the complex. Similarly, another possibility, that is, we have no real root, you have completely complex root in conjugate pairs, like I gave the example here. Okay, roots are in the conjugate pair, but that is possible only the case when you have all real coefficient. This is the idea behind the complex conjugates in case of roots. Now in case of degree 3 equation, we are having three roots. It is also known as the cubic equation, and there are again three possibilities. You may be having all three roots real. The curve is intersecting the x-axis at three different points. Another possibility that you have one real root and two roots are complex in the form of conjugate pairs if you have all real coefficients. Note down this important, very important property. You can't be having three complex roots. You can't be having just one complex root. You have the complex root in pair, but the condition says you must be having all real coefficients. And finally, the third possibility, that you have the real root, but there are two real roots in appearance. Why? Because one root is being repeated. There's a point where the x-axis becomes the tangent. So that's why we can say we have just two roots. In fact, there are three roots, but two roots of having equal values. In case of yes, there's no other possibilities. In case of degree 4, you have four factors. It means you're getting four roots. There are four possible points where the curve cut the x-axis. Like here, we may be having the first possibility, all four real roots. There are possible two real roots, but two complex roots in conjugate pairs. The another possibility that there are four complex roots, but in the form of two pairs. For example, 2 plus iota and 2 minus iota and 3 plus 4 iota and 3 minus 4 iota. We get two pairs of complex roots, not one pair, two pairs. And again the same condition, the complex conjugates are there if all the coefficients of in the equation are real. There's another possibility here. We have three real roots. Suppose if you have a tangent like this here, in that case you can say one root is being repeated, so total we are having three roots. You got the idea? These are the few things, important things about the roots of polynomials in case of this complex study. Now another important thing, sometimes the roots are there. For example, you have the equation 3 having roots 3 and 5. We have the equation with roots 3 and 5. If I go backward, I can write the factors x minus 3, x minus 5 is equal to 0, because I can get the same roots. If I multiply them, I get x square minus 5x minus 3x plus 15, and similarly you get the equation. So please learn this technique as well. So if you have the equation starting with the quadratic with roots alpha and beta, suppose if I'm multiplying, here I am getting the coefficient of x as negative times sum of alpha beta, and the constant becomes the product of roots. See here, note down this property. Whenever you have the roots, you don't need to show the complete stage. You can just jump directly with this formula. X square minus sum of roots, you get 8x, and the product you get 15, get the answer. This way you can move backward if the roots are there. Now if the roots are complex, then what happens? And you know the complex roots are in conjugate pairs. So in place of alpha plus beta, you must be writing z plus z conjugate. In place of alpha beta, you are multiplying these two roots. And we have done in the lecture number 1, when the roots are added in conjugate pairs, you get twice of real, and when multiply you get x square plus y square, or you can say square of modulus. Please note down these key properties. This way you can form the equation with the known roots, and in examination you will find question based on this concept. Now starting few examples. For example, here I have 1 plus 2 iota, one of the roots, and I know the other root is, they are saying real coefficient, other root must be 1 minus 2 iota. You want the equation, you know the formula, x square minus sum of roots, that becomes twice of real, so 1 plus 1 2, that's it. And the product of roots become x square plus y square, 1 square plus 2 square, that is 5. A very smart way to get the answer quickly. You see here, learn this technique, practice this idea. Suppose if I have an equation whose one of the roots is 1 plus 4 iota, right? So other root should be 1 minus 4 iota, 1 plus 4 iota, and 1 minus 4 iota. We have these two roots. Now find the equation. How to find the equation? X square minus twice of real, so you can write 2ax, plus the product becomes x square plus y square, so we have a square, and in place of y we have 4 square 16. That is the equation. Simple as that. Hopefully the idea is clear. I'm leaving all these questions for you. Try it yourself, do it yourself. Okay, now I'm doing one more example for you. That is, if you have one of the roots minus 4 plus iota, and you are looking for the other roots, how to find those roots. So you know the other roots are, one of them is complex conjugate because you have all real coefficients. The equation here, first of all apply that concept I showed in the last slide. X square, the quadratic factor, minus twice of real when you multiply in conjugate pair, so minus 4 twice means minus 8, plus x square, y square, 4 square 16, 1 square 117, and multiplying with ax plus b is equal to what? X cube plus 4x square minus 15x minus 68. X square plus 8x plus 17 ax plus b equals to x cube plus 4x square minus 50x 68 minus 68 here. Now if you multiply x square with ax, you get ax cube, and here you have x cube, so a becomes 1. 17 times b is 17b, remainder factor theorem all of you should know, and the constant there is minus 68, so b becomes negative 4. So your factor will be 1x minus 4. So when 1x minus 4 is equal to 0, x becomes 4. So what are the roots? Minus 4 plus iota, minus 4 minus iota, and 4. See the answer here. So please do these questions yourself. Now moving to the next idea. If you multiply two complex numbers and you are getting a new complex number, what happened to the modulus of new complex number? And what happens to the argument of that complex number? And we have done this lecture number 1. I'm just showing here the proofs of this by using the polar coordinates or polar form. The proof is not must for each and every student. Those who have curiosity, those who have good understanding of trigonometry, they can go through these slides and get the idea why the arguments being added and modulus being multiplied. Here I have taken one complex number as z1 in the polar form, other complex number as z2 in the polar form. I multiplied the two complex number r1 into r2 here, cos theta 1 into cos theta, sorry, this is cos theta 2 into cos theta. I think there's a mistake here, typing error. That must be 1 here. Sorry, I'm mistaken. So cos theta 1 into cos theta 2, then cos theta 1 into iota sin theta 2, and so on. Then you apply the formula cos A cos B minus sin A sin B, and sin A cos B plus cos A sin B. You know the trigonometric identities, and you get these results. This proof is not mandatory for each and every student, but there's a proof of every property, obviously. I've shown here for those who have curiosity to know why this happens. Similarly, these are the same thing. If numbers are being divided, again you apply trigonometry here. Your two complex numbers are z1 and z2. If you divide them like this, and you have here your imaginary number, multiply and divide by the conjugate of denominator. You see, I multiply and divide by cos theta minus iota sin theta 2. You see here, that will change your denominator to real number. A minus b plus b is a square minus b square. Iota square is minus 1, that by plus here. And sin square plus cos square is 1. Ultimately, you're getting this result. And you see here, the modulus are being divided and arguments are being added. So it's subtracted. So please learn these properties mainly. Not the proof. Proofs are there for only those who have curiosity to know. Otherwise, you learn the properties and how to apply in different questions. Next point, this we have discussed. It's an idea with the name of Demovers Theorem. If you have a complex number in the polar form or the modulus argument form, as you see on the screen here, r is the modulus, theta is the argument, and if I apply this concept I did in the last few slides, if z1 and z2 both are z into z square, so modulus becomes r into r square, and argument being added, argument of z plus argument of z becomes twice. You see here, when the power is 2, modulus accept the power, but argument multiply with the power. If the power becomes 3, the modulus having the power 3 and argument multiply with the power. If the power becomes n, this statement is known as Demovers Theorem. Very interesting. The whole syllabus of complex number, further mass complex number, based on this big idea of Demovers Theorem, and we apply in so many a variety of examples and cases Demovers Theorem. But here you should learn this property only. Okay, whenever a complex number, suppose a complex number 1 plus iota, and you want this, there are two ways. One of the ways is to expand with the binomial. Second way is, for this complex number, find the modulus, that is root 2, find the argument, that is tan inverse 1, and what is tan inverse 1? Pi by 4. Now you know the modulus and argument. You want z power 4. So modulus raised by the power. Root 2 power 4 becomes 4. Argument multiply with the power. So pi by 4 into 4, because the power is 4. Pi by 4 into 4 is pi. Cos pi, iota, sin pi. Cos pi is -1, sin pi is 0, and you got quick answer, that's it. Please try to apply this theorem with the name of Demovers Theorem. So please digest this idea and learn this property. Whenever you raise a complex number by any power, its modulus is same as first you find the modulus of original complex number and raise by the power. There is no need to expand completely and find the power. You can learn the property, and we derive this from Demovers theorem. And whenever a complex number raised by any power and you are looking for the argument of this new complex number, it is same as the argument of original complex number times n. For example, if complex number is 1 plus iota and I want the argument of z power 10, there is no need to expand. The argument of this complex number is, we have done pi by 4 times 10 and you get the result. Right? This is the property you should learn. Now the last thing here, complex number in the exponential form. We have done complex number in the standard form, you know it, and then we found the modulus and argument. We have done the complex number by knowing the modulus argument in the polar form or modulus argument form. The third way of writing complex number, the proof is not the part of P3 syllabus, beyond its scope of P3 syllabus. Those who are doing further maths, they know how to prove this with the help of Maclaurin series, right? I can replace this factor cos plus iota sine by e iota theta. This is the exponential form of complex number. And this form is very convenient for a variety of proof. For example, if I'm saying z1 into z2 and my z1 is r1 e iota theta 1, my z2 is suppose r2 e iota theta 2, we are multiplying here r1 into r2, multiply them, base same, powers added. You can simply prove that property that when complex numbers are multiplied, modulus are multiplied and arguments are added with this exponential form. You got the idea clear? Similarly, if z is equal to r e iota theta, remember this point, when you're looking for the conjugate, modulus remains same. If you know the lecture number 1, we have done this property for complex conjugate, we have the same modulus but the argument having negative sign. See here, this way you write the complex conjugate in the exponential form. And with any power here, z power n, for example, you want the square root. If you want the square root of z, suppose z is given 9 e iota, suppose pi by 6 in this form. Examiner is asking find the square root. There are two ways. First, you write this form in the polar coordinate, replacing r by 9 and theta by pi by 6. Expand it, you got the standard form. Then apply the complete method of square root which we did in the lecture number 1. That's a possibility. A quick and smarter way in the exponential form, if you have the exponential form, you just raise it power by half. 9 power half is 3 and pi by 6 into half is pi by 12. And if you remember my first lecture, I've told you there that the square roots are always by a difference of 180 in terms of angles. Remember, when you're writing the second square root, don't write plus or minus with the number. This is wrong. Or don't just change the sign of the power, that becomes the conjugate. The second square root having the same modulus, but its power it differ by pi or 180. So in pi by 12, if I subtract this part minus pi, what do you get? Negative 11 pi by 12. Note down this. If you're still having confusion in this concept, you may ask in my live session. Is that clear? These two are the square roots, and such question was tested in the examination few years back. Clear? A very quick summary of complex number I've discussed just within hardly 2 hours in these lectures, or less than 2 hours. It's a detailed topic. I've told you at the beginning, I'm just revising or giving a summary of the chapter, but comprehensive, and try to cover most of the properties. One idea is left I want to share here, because a question was asked a few years back about this property and most of the students found it difficult. What happens when you multiply a complex number by iota? For example, 2 plus 3 iota, multiply by iota. What do you get? Minus 3 plus 2i. So the property says if you have a complex number here, suppose z, multiply with I, that number becomes z into I. There's an important property here. If this angle is theta, this is rotated anti-clockwise by pi by 2 radian. Note down this. Whenever you multiply a complex number by iota, the angle is rotated by, moved by anti-clockwise pi by 2. Again multiply by z in iota into iota, iota square is -1, you are here. Again this angle is pi by 2, and you see this is iota square into z, and iota square is -1. Again multiply by iota, you are here, because iota cube is there, and iota cube is minus iota, and again this angle is pi by 2. Note down this property. Whenever multiplying a complex number by iota, anti-clockwise transformation, rotated by anti-clockwise angle of pi by 2, and the modulus remains same. You see, the distance from the pole remains same. It's moving about the pole anti-clockwise. So angles changing by pi by 2, pi by 2, and pi by 2. Note down these properties. Please go through these lectures before joining my session on 6th of April. Thank you, dear. And these are few practice questions I forgot to discuss, but I'm showing you here. You pause the video and you try to solve using Demovers theorem or whatever you want technique, and you can discuss. If you find difficult, you can discuss the solution of these questions in my live session. Thank you. Allah Hafiz. Enjoy learning.